Hello friends, so welcome to this lecture on matrix algebra. So like vectors, matrix also is an essential part of machine learning. Most of the data sets we represent in form of a matrix. So in this lecture we will learn some basic operations between matrices. So first of all let me define matrix in a layman language. So a matrix is a two-dimensional array of scalars. These scalars may be complex numbers, these scalars may be real numbers, these scalars may be some categorical variable. But here we will focus on real numbers, means matrix of real numbers. So a matrix is a two-dimensional array of scalars with one or more columns and one or more row. As I told you, it is a very layman definition. The classical definition of matrix we will cover in subsequent lectures after introducing the vector spaces. So, for example, if you can see this particular two dimensional array, so it is a 3 by 3 matrix. It means the first index is for the number of rows and second index is for number of columns. In this way it is a 2 by 2 matrix of real numbers. It is a 3 by 1 matrix which is nothing just a column vector, and it is 1 by 3 matrix which is a row vector. So, usually we denote the elements of a matrix by Aij, where I is 1 to m and j is 1 to n. So, it is a m by n matrix, m number of rows and n number of columns. So, for example, if I talk about this one, so here A11 is 5, A12 is 8, A13 equals to 7. Similarly, if I say about this entry, it is an entry in third row and second column. So, it is A32 which is equals to 0. So, in that way we represent the elements of a matrix. Now, I will introduce you some special types of matrix. So, first one is diagonal matrix. So, in a diagonal matrix all the off diagonal elements are 0. So, for example, it is a 3 by 3 diagonal matrix. If you check, these elements are diagonal elements, means diagonal elements for which I equals to j, means A11, A22, A33, and all these elements are off diagonal elements. So, you can see in this matrix all the off diagonal elements are 0. If you see, it is a 0 matrix of order or size 3. In a 0 matrix all the entries are 0, and again it is a diagonal matrix, because I am saying in a diagonal matrix all the off diagonal elements are 0. So, here if you see in this matrix all the entries below main diagonal are 0. So, it is an upper triangular matrix. Similarly, if you see this particular matrix, here all the entries above main diagonal are 0. So, it is a lower triangular matrix. Now, another important matrix which we will use quite frequently is identity matrix. So, an identity matrix is a diagonal matrix where all the diagonal entries are 1. So, for example, a 2 by 2 diagonal a 2 by 2 identity matrix is this one. So, it is I represent by I 2. Similarly, I 3 is 1 0 0 0 1 0 0 0 1. So, you notice that diagonal these identity matrices are square matrices of any order, okay? Because in case of rectangular matrix we cannot talk about diagonal element and so on. So, it is identity matrix. Now, come to some operations like addition, subtraction, multiplication between matrices. So, two matrices are said to be equal if their dimensions are equal and all corresponding elements are equal. So, for example, if I take a matrix A 1 minus 1 2 3 and the same time I take B which is again 1 minus 1 2 and 3. So, here if you see both are 2 by 2 matrix, the A11 equals to 1 which is equals to B11, A12 is minus 1 equals to B22. So, in that way Aij equals to Bij for all I and j, means I equals to 1 and 2, j equals to 1 and 2. So, hence both of these matrices are equal. If suppose instead of 3 this entry becomes 0, then you can see A22 not equals to B22, because here it is 0, it is 3. In that case A is not equals to B. Okay. So, in that way we can say whether the two matrices are equal or not. First of all, they should be having equal size. Secondly, all the elements of matrix A must be equal to the elements of matrix B. Now, come to the addition or subtraction of two matrices. So, suppose I am having a matrix A, another matrix B, which are of same size, which is the necessary condition for performing addition or subtraction between two matrices. Okay. Then the resulting matrix C will be of the same size and the entries of C, which is I am denoting by Cij, must be equals to Aij plus Bij in case of addition and Aij minus Bij in case of subtraction, and this is for all ij, means in addition we are adding the respective elements of those two matrices, whereas in subtraction we are subtracting the respective elements. So, for example, I take A equals to 1 minus 1 3 2 0 1, which is a 2 by 3 matrix. I am taking an example of rectangular matrix. I am taking B equals to 1 1 0 2 1 3. Then A plus B equals to 2 0 3 4 1 4, means how this 2 is coming 1 plus 1, how the 0 is coming minus 1 plus 1 and so on. So, I am adding the respective elements of A and B. Similarly, A minus B equals to 1 minus 1 0 minus 1 minus 1 minus 2 3 minus 0 3 2 minus 2 0 0 minus 1 minus 1 and 1 minus 3 minus 2. So, here you can note down A plus B equals to B plus A, means matrix addition is commutative, whereas A minus B may not be equals to B minus A. More, the matrix addition is also following the associative law. That is, if you are having 3 matrices A, B and C, you add first B and C and then add A, which must be equals to adding first A and B and then C, and which is equals to A plus B plus C. So, in addition, ordering of matrix order of matrices does not matter. Okay. Now, let us see the scalar multiplication, means when we multiply a matrix by a scalar. So, let me take a matrix A, which is A11, A12, A1n, A21, A22, A2n, and then AM1, AM2, AMN. So, it is a m by n matrix. Now, if I take a constant alpha, which is a real number, then or it may be a complex number also. So, it is a scalar, then alpha times A will become, I will multiply this alpha into each and every element of this matrix. So, alpha A11, alpha A12, alpha A1n, alpha A21, alpha A22, alpha A2n, and then finally, I will be having alpha A M1, alpha A M2 and alpha A Mn. Okay. So, in that way I can define scalar multiplication with a matrix. So, for example, let me take an example here. You take A equals to 2, 1, minus 1, 4, and let us take alpha equals to 5, then 5A will become 2 into 5 10, 1 into 5 5, minus 1 into 5 minus 5, 4 into 5 20. So, like this. Now, come to the most important operation, that is matrix multiplication. Okay. So, again the product of two matrices is another matrix. However, here we are having some conditions. We cannot multiply matrices arbitrarily. There should be some condition which must be satisfied. So, what is that necessary condition? So, the necessary condition for multiplication of two matrices A and B is that the number of columns of A, if you are multiplying A with B, then number of columns of A must be equals to number of rows of B. Okay. And if you are multiplying B with A, then in that case number of columns of B must be equals to number of rows of A. So, it may happen AB is defined, but BA not. So, whenever we are multiplying two matrices, the number of columns of first matrix must be equals to the number of rows of second matrix, otherwise we cannot multiply those two matrices. Okay. So, for example, here if I take a matrix A of order 5 by 3 and B of order 3 by 4, then the output matrix C will be of order 5 by 4. Okay. So, you see this is the number of columns in A, this is number of rows in B, they are equal. So, you ignore these two, and whatever outer dimension are there of A and B, that will be the dimension of matrix C, which is the resulting matrix. Okay. So, if I say here what will be B into A, so B is of size 3 by 4, where A is of size 5 by 3. So, here number of columns in B is 4, number of rows in A is 5, means number of rows in A is 5. So, these are not equal. So, this is not defined. We cannot multiply B with A here, whereas A B is well defined. Okay. So, now how to compute this multiplication, how to compute this resulting matrix C when the matrix multiplication defined. So, for example, see this example. So, for that see this example. So, it is a 2 by 3 matrix, it is a 3 by 2 matrix. So, let us say it is A, it is B and it is C. So, obviously, the output matrix will be of size 2 by 2. Now, how to compute the entries of this resulting matrix? So, what will be C 11? So, for calculating C 11, you take first row of the matrix A. So, it is a row vector A 11, A 12, A 13. Multiply it with the first column of B. So, B 11, B 21 and B 31. So, both are vector and this is nothing but dot product of these two vectors. So, it comes out to be A 11 into B 11 plus A 12 in A 12 into B 21 plus A 13 B 31 and this is your C 11. So, when I am defining some Cij, you take the ith row of A and take the dot product of the jth column of B, okay, and that number, that scalar which you are obtaining after this dot product will be Cij. Okay. So, for example, A 23 will be C 22 will be the dot product of second row of A and second column of B. So, let me take a very small example. Suppose I am having a 2 by 2 matrix 1 minus 1 2 1 which is A and I am having B which is 2 by 3. So, 1 minus 1 0 0 1 1. So, 2 by 2 2 by 3. Okay. Now, the resulting matrix C will be of size 2 into 3. Matrix multiplication is well defined because number of columns in A equals to number of rows in B. So, here C will become, you take the first row. So, let me work out here first row of A 1 minus 1 and take the dot product of first column of B which is 1 0. I am writing in row form. So, in row vector form. Okay. So, it will become 1 into 1 1 plus 0 equals to 1. So, it is 1. For calculating this entry, you take the first row because it is C 12. So, for C 12, C 11, C 12, first row of A and take the dot product with second column vector which is minus 1 1. So, it is minus 1 equals to minus 2. Then in that way I can calculate this entry as 1 into 0 plus minus 1 into 1 as minus 1, 2 minus 2 plus 1 minus 1 and then 1. This will be the resulting matrix C. Now, there are some rules for matrix multiplication. If you multiply a matrix with identity matrix and matrix multiplication is defined in that case, then A into I equals to I into A equals to A. Matrix multiplication follows the associative law. It is also follows the first distributive law, means if you take the addition of B plus C and whatever resulting matrix you are getting after this addition, you are pre-multiplying with A, it will be equals to AB plus AC, means first you multiplying B with A and C with A and taking the addition. It is also following the second distributive law, means post multiplication with the addition of matrices. Whereas, there are some remarks also, means some questions. AB not generally equal to BA, and we have seen the example where AB is defined, but BA is not defined. Okay. If you are having two numbers, let us say x and y in case of real numbers, and x y equals to 0. So, we will be having either x 0 or y 0, but this kind of reasoning is not true in case of matrices. If the product of two matrix is a 0 matrix, then it may happen that neither A nor B are 0. So, for example, you take two matrix 1 0 0 0 and 0 0 0 1. So, none of these two matrices are 0, but their product, if you calculate 1, it comes out to be 0. So, this is an example of this where A B is 0, but neither A nor B is 0. If A B equals to A C, then it may happen that B is not equals to C. That is, if you are having real numbers and you are saying that alpha x equals to alpha y, then and alpha is non-zero, then we will say that x equals to y. So, here if A B equals to A C, it may happen that B not equals to C. Then we are having a concept of transpose of a matrix. So, transpose is nothing if you are having a matrix A whose entries are represented by Aij, I equals to 1 to m, j equals to 1 to n. So, it is a m by n matrix. Then transpose of A is given by this notation A superscript T, and it is nothing just A j I. So, transpose will be of order n by m, where A is a of order of m by n. So, what we are doing? We are just interchanging first row with first column, second row with second column, and so on. So, for example, if you are having A equals to 1 3 2 1 and 1 minus 1, let us say 3 by 2 2 by 3 matrix, then A transpose will be a 3 by 2 matrix, which is 1 2 3 1 1 minus 1. Okay. So, what I am doing? My first row is 1 3 1 in A. I have made it first column of A transpose. Okay. Second row is 2 1 minus 1. I have made it second column of the A transpose, or in other words you see first column is 1 2 in A, it is now first row in A transpose. So, some rule, if you are having two matrices A and B, so A plus B transpose equals to A transpose plus B transpose, whereas A into B transpose equals to B transpose into A transpose. If you are having a scalar k, then k times A transpose equals to k into A transpose, and then transpose of a matrix equals to the matrix itself, means A transpose equals to A. So, then we are having determinant of a matrix. So, every square matrix has a determinant. The determinant of a matrix is a scalar, okay. So, it is a real number or complex number, okay, depend on the nature of a matrix. Now, if I am having a matrix, let us say 2 by 2 matrix 1 minus 1 2 3, let us say A, then determinant of A is denoted by this symbol or det of A. So, it will become, you multiply these two. So, 1 into 3 is 3 minus multiplication of these two. So, 2 minus 1 equals to minus 2. So, 3 minus minus 2 equals to 5. Now, there is another important concept, that is inverse of a matrix. So, every square matrix is not invertible. If the determinant of a matrix is non-zero, then only we can find out the inverse of that matrix. So, means if determinant is 0, we say the matrix is singular. If determinant is non-zero, we say the matrix is non-singular. So, if a matrix is singular, inverse does not exist, whereas for non-singular matrices we are having the inverse. Now, if I am having a real number, let us say, or a scalar k equals to 7, then the inverse of k is 1 by 7. So, here if I take k equals to 0, in that case 1 by 0 is not defined. So, similarly, if the determinant of a matrix is 0, the inverse of that matrix is not defined. Okay. So, the inverse of a square matrix, say, if it exists, is the unique matrix A inverse, such that A into A inverse equals to A inverse into A equals to I. So, for every non-singular matrix A, there exists another matrix B, such that A into B equals to B into A equals to identity matrix of that size. Then we will say B is inverse of A. So, if B is the inverse of A, then A will be the inverse of B. In case of inverse, we are having some rules. The first one is, the inverse of A into B will be B inverse into A inverse, and these rules we are saying if inverse exists. The inverse of A equals to A itself. The inverse of transpose of A equals to transpose of inverse of A. So, you can interchange the order of inverse and transpose. If you are having a scalar k, and then the inverse of k times A equals to 1 by k into A inverse. So, these are some rules in case of inverse. Now, we will see quickly the implementation of these operations in Python. So, again I am using Google Colab. So, I have opened a new notebook in Google Colab. Okay. So, like the case of vector, we will import numpy as np, because we will use many linear algebra functionality here. Then I am defining a matrix P. So, like we have defined the vector, I am having it is a numpy array, and now matrix is a 2D array. So, I will use this for the overall matrix, and now each row I will define as a vector. Okay. So, let me take 1 7 as the first row, 2 1 as the second row, and 3 2 as the third row. Okay. So, if I print P, yeah, so you can see here it is a 3 by 2 matrix. Let me define again a matrix Q. So, let me take it 1 1 comma 1 minus 1, and then let me run it. So, I have stored it. If you want to see it, it is print Q to print this matrix. Okay. Now, let me add P and Q. So, let me define a matrix C 1, which is addition of P and Q. So, again for adding I will use the command np dot add, and then I will pass my matrix P and Q. So, let me add it. So, you can see the error. So, what is the reason? That the size of P is 3 by 2, whereas size of Q is 2 by 2. You can add P and Q only when the size of both the matrices are same. So, let me modify this Q now. See the new Q. So, it is again 3 by 2, which is similar to P. And now, let me define this addition and print C 1. So, C 1 will be a new array of the same size, that is 3 by 2. So, if you see 1 is added with 1. So, 2, 7 is added with 1, 8. So, we are having matrix addition. Similarly, you can define subtraction by using subtract. So, you can see, so it is nothing, 1 minus 1 0, 7 minus 1 is 6, and so on. Now, let me define the multiplication. Okay. So, let me here it is P is 3 by 2, Q is 3 by 2. So, their multiplication is not defined. Okay. So, let me take a matrix R, which is let me take 3 by 2. So, of size 2 by 3. So, 1 3 1 is the first row, and second row let me take 1 0 1. Okay. So, now this is my matrix R. If you want to see this R, print R. So, you can see R is a 2 by 3 matrix. Now, the number of columns in P is 2, whereas number of row in R is 2. So, both are equal. I can define P into R. Okay. So, let me store it in C 2. So, again np dot P into R and print C 2. So, you can see it is 8 3 8 3 6 3 5 9 5, which is a 3 by 3 matrix obviously. 3 by 2 into 2 by 3 will be 3 by 3. Okay. Now, let me define a square matrix, let us say C2 is there. So, how to calculate the determinant of C2? So, dit equals to np dot dit so not np dot dit like add subtract, here you have to come use linear algebra sub package of numpy. So, it is you have to write lin alg dot dit and then you will be having I am calculating the determinant of C2. I need to print dit. Yeah. So, you can see determinant is 0, it means C2 is a singular matrix. If I calculate the inverse of C2, so let me take in S2. So, NP dot lin alg dot INV of C2. So, I will get an error because it is a singular matrix. Yeah, so you can singular matrix, that is why inverse of C2 does not exist. So, let me define a very basic 2 by 2 matrix, let us say M equals to NP dot array and which is, let me write 1 minus 1 and then 2 3 and then now let me calculate the inverse of this M. So, print np dot lin alg dot INV for inverse and inverse of which matrix? M. So, let me check. Yeah. So, this 0.6.2 minus 0.4.2 is the inverse of M. If you multiply M with this matrix, you will get identity matrix of 2 by 2 in any order. Now, we are having lot of usage of matrices in machine learning. In fact, we will use it in most of the algorithms. Okay. So, with this let me close this lecture. Thank you very much.